Right. I want you to know that this is work done by me and Lenore, who is sitting over there. And uh, we're trying very much to get into the hard problem. So let me, oops, why am I not able? Oh, good. Thank you. So let me just quickly say something about me. When I was in second grade, my teacher told my mother that I might be able to get through high school, but don't expect I can get to college, which made her very sad. But it got me asking my dad, well, what can I do to be able to remember stuff? What can I do to be smarter? And he told me, after I pestered him a lot, he told me, if you understood what's in your head, you could be smarter. And I thought, wow, what a great idea. I can remember in the fourth grade walking in the garden trying to introspect what's in my head. And it didn't work. It just felt like there was a homunculus in my head looking out through my eyes. And I understood that that's not going to work. Fortunately, I did get to MIT. And in my junior year, I was told that, Dr. Warren S. McCulloch had come to MIT. And in my junior year, I asked him to be my mentor. And I am so fortunate that he eventually agreed. I remember, so by the way, McCulloch is the person who first defined the formal neuron. And McCulloch and Pitts are the ones who then proved that you could build a Turing machine out of these formal neurons. It's really interesting that the formal neurons, he talked about, had both positive excitation and negative inhibition. And the neuroscientists at the time were not that convinced about the inhibition. They said, we haven't found that yet. But McCulloch said it has to be there. McCulloch was a very, very wonderful and supportive person. Anything I wanted to do, he would encourage and support me in doing. Until maybe a month or so or two after I started working with him, I told him that what I really wanted to do was to understand consciousness. And as supportive as he was, for the first and only time in his life, he put his finger in the air and said, "You will not work on consciousness." I'm very lucky that maybe 10, 15 years ago, Lenore told me, you can start working on consciousness. We can start working on consciousness now. There's enough known. So we can start working on consciousness. Our approach is from theoretical computer science. Lenore is a mathematician, theoretical computer science. We tried many models. When one didn't work, we threw it out and tried another. We wanted a very simple model that would enable us to understand consciousness. It's like Turing had this. Turing machine was a very simple model of what's computable. We wanted a correspondingly simple model of consciousness, something that would help us understand it. So we tried many models. We would try a model, and then in order for it to work, it had to be made more and more complicated. We threw it out, tried another one. And this constantly happened until finally we hit on the CTM. And when we finally hit on this conscious Turing machine, we challenged our students to suggest improvements. And so we taught at Carnegie Mellon. We're actually now chair professors at Peking University, which has maybe the smartest students we've ever taught. So we challenge our students to suggest improvements. And they do come up and suggest improvements, but those improvements will, most of the time, we just can say, look, you don't need to make this change. The model already works to do that. So in every case, we show it's not necessary to add complexity to the model. It's not necessary to modify the model. So we taught classes, we challenged our students. This is the beginning of the talk. I was just trying to see if I could make do with, the single line that people tell us to, but anyway. So here's the abstract, what we mean by consciousness, and then an informal description of the conscious Turing machine. Very informal, then a formal description, or at least I'll tell you that there is such a formal description. How we check that the conscious Turing machine is a good model. And finally, the insights that we can give on the hard problem of pain. So the way this works is Lenore and I, everything I say could be given to you by both of us. And we've decided to split the problem of pain and pleasure. Lenore works on pleasure, I work on pain. That's each of us on what we want. So I want to say we gratefully acknowledge Michael Schwan for his support and encouragement, in the beginning especially, very important. Kevin Mitchell for his 15 questions that he said any good model of consciousness should be able to answer these questions. And Vanya has just told us that there's even something better that we could refer to. And so thank you. I put down Vanya Visa into this slide before I knew that he would be presenting it. So anyway, so let me just tell you very quickly the Baars Theater Model. You perhaps know it already. Consciousness is the activity of actors in a play performing on the stage of working or short-term memory. The spotlight is on a single actor speaking to the audience. Actually, he has a whole play going on with the spotlight, but that's okay. The performance is under observation by a huge audience of powerful but unconscious processors in what we call long-term memory that are sitting in the dark. This idea, when I found out about it, I realized this is exactly what I was looking for when I was in the 4th grade. It's so wonderful to be able to say, hey, I can tell that 4th grader what he wanted to know. Let me start by just quickly, this is as far as I'll go into telling you about the CTM. You see Baars' model on the left and the CTM on the right. In Baars' model, the inputs come in and they go directly to the stage, and from the stage, they go to the output. In our model, we don't have that. In the CTM, the inputs come to processors that turn those inputs, what you see, what you hear, into something we call chunks. And all that all that the CTM is ever conscious of is those chunks. The CTM does not actually see the outside world. It is only aware of those chunks. So the inputs come in, they go to processors that convert those inputs into chunks, and then finally some processor sends chunks into instructions to the arms and legs. So there's a difference with Baars. There's the stage. There's the long-term memory processors. I've already told you input output directly. Ours is a little different. Conscious event in Baars is between the input and the short-term memory. In ours, conscious attention is reception of the broadcast. So what goes on is the processors are trying to have information. They have weights on that information, and then there's a competition to decide what will get up to the stage. And of course, there's the question of how those weights are set. We're very lucky that that's an important problem. And we mentioned it to our son Avram, and he said, I have a paper on it. I have just what you need to know. It's actually called Sleeping Experts Problem. It's not so easy for him because in his Sleeping Experts papers, there's a teacher who has questions and knows the answers. And in the CTM, there's nothing like that. The teacher is replaced by predictions. Every processor that is trying to get something up on the stage predicts what will come, predicts what the effect of what it's saying would come. And when it finds out what comes, that well, it finds out could be maybe it would discover that it is correct in what it thought would happen, and its weight can go up. Or maybe it discovers it was wrong, in which case its weight goes down, and it modifies the algorithm so that it'll be better the next time. That's okay, conscious attention. Baars has no specific method for the information in long-term memory to get up to short-term memory. He says the processors get together to decide what should go up. That's not enough for us. We have a well-defined competition for chunks to get into short-term memory. I'll be telling you what a chunk is and what that competition looks like. In Baars, there's no model of the world. We do have a model of the world. Here's something interesting. Baars has a central executive. Every model, every theater model that we know of has a central executive. We do not have a central executive. You know, this, if there's a task to be performed, the central executive would have to know who to assign that task to, which processor. Some processors are already doing a lot of work, some processors not. Some processors have some abilities, some algorithms that would be useful, others not. You really can't expect the central executive to keep up with this knowledge. So what we have is no central executive, we have a federation. Okay. So let me give you some idea of how this works. For this idea, I'll tell you how the CTM works when an infant is born. I'm going to assume that the infant is born with a CTM brain, okay? And this is what happens. So the infant is born. It's got all these processors. Those processors don't know anything. They are not linked together. They are basically know-nothing processors. There are some that are concerned with input, which they turn into chunks, with output, and others are like gauges. You know, there's a gauge for hunger. When you get hungry, that gauge starts to say, hey, I need to eat. So here's the newborn infant. It's born, and all of its processors, whatever they have, they have like a weight of 1, more or less, plus or minus 1. Weights can be positive, pleasure, or negative, pain. Okay, so these processors will initially have weights of plus or minus 1. But there is a gauge there that is a gauge for oxygen. And that particular processor, that gauge for oxygen, starts to realize it needs some oxygen. So it raises its weight until it gets on the stage. And from the stage, it broadcasts to the entire audience, I need oxygen. And nothing happens. It raises its weight, I need oxygen. The processors have no idea what to do. They're just born. They have nothing. They have absolutely no idea, but built into every processor is do something. And in fact, the processor that controls the arms and the legs will flail the arms and the legs. The processors will cause the infant to pee and poo. Anything that a processor could force the infant to do, it does, until finally the infant cries. And when the infant cries, it gets the oxygen. And so that's how the CTM infant is born. Let me mention that the first word that the infant puts into its language, which we call brainish, that first word in this case is pain, or pain for the lack of oxygen. It takes it takes the fact that this pain had a very great weight, and that becomes its first word. The second word will be crying helped. And the infant will learn every time when it's hungry, whenever it needs anything. Crying helps. And for a very long time, that uh, crying is the way the child gets what it needs. Let me tell you something about the competition here. Here's a competition between eight different entities. And let me show you how it works. The numbers you see here, 3.14159, these random looking numbers are the weights that these processors have attached. I've left out the minus signs because it would, in the competition, they're replaced by pluses. So the way it works is that A and B compete to decide which of them will win. And the competition is probabilistic. A wins with probability. Every processor is going to win the whole competition with probability proportional to its weight. This is interesting because tennis has such competitions. Chess has such competitions. They do not have the property that a player wins with probability proportional to the weight. This CTM does. And it works like this. It's a winner-take-all competition. When two players play each other, the winner gets all of the losers' weight. In chess, the winner will have a certain ELO rating, and that ELO rating will be increased by a small fraction of the losers. But here, the winner takes all. And this is very useful because it gives you this theorem that the player wins with probability proportional to its rate. So here's whichever of A and B wins, its weight will be 4. And similarly, whichever of C and D wins, its weight will be 5. And then between those two winners, the new weight will be 9. And you see this simple addition runs through the whole thing. And that will help us. Let's look at what's happening here. When I'll look at F. Okay, there's F over there in blue. Let's see what's the probability that F wins the competition. Well, it's the first match will win with probability 9, its weight, divided by 5 plus 9, which is 14. So the probability that F wins at the first round is 9/14. At the second round, the probability it wins is 14, its weight, divided by the sum of it and then the loser's weight, 22. That's 14 divided by 22. The next round, it'll be 22 over 31. The probability that F wins the tournament, the whole tournament, is now 9/14. The probability won the first round times 14/22, the probability won the second round times 22/31, the probability won the third round, and you see these cancel and you get 9/31. So it's quite, I love that winner take all. It's great. Okay, so a corollary of this is that in a winner-take-all competition, it doesn't matter who plays who. The probability of processor winning is proportional to its weight, no matter where, no matter who it plays against. So that's a big advantage because particle processors, they can't be moved around. So, okay, so this concludes part 1 of the 4 parts in this lecture. Okay. Any questions? You're welcome to ask. You don't have to wait till the end. Okay. Okay. So formal definition. Why do we need a formal mathematical definition? The point is that with a formal definition, one can argue for or against. You may like it. You may dislike it. You don't like it, you can start to argue. There's no question of what's going on. That's part of why one wants a formal definition. So here is the formal definition. Time is measured in clock ticks, 0, 1, 2, 10 to the 7. 10 million clock ticks in the life of the CTM. It's not a Turing machine. It's not something with infinite life. It's a very finite lifetime. We're assuming 10 ticks per second, which is the alpha rhythm of the brain, and or up to 100 ticks per second, which is the rhythm when you're really thinking very hard, the beta and gamma rhythms. But in this formal definition where everything is defined precisely, we take it to be 10 ticks per second. The CTM is born at time 0 and dies at time t, which at 10 ticks per second is about 33 years. That's okay. CTM has a number of processors, n, which is also 10 to the 7. And there's a reason for that, that the number of processors is equal to the number of ticks. And I won't go into that. So all processors are in long-term memory. Yes, that's the point. All processors are down below in long-term memory. There's no processor up in short-term memory on the stage. No, none at all. The stage is only, it receives the winner of the competition, and it's a broadcaster. It simply receives it and broadcasts it to all the audience. That's so there's not even a processor there in short-term memory. Okay, so now in a formal definition, we computer scientists, mathematicians like to state CTM as in this case, as a 7-tuple. STM, LTM, up tree, down tree, links, input, output. STM is the small memory at the top. I'm going to go through this very fast. STM is a small memory. LTM is the massive parallel collection of powerful random access processors. They're not even Turing machines. They're random access. A Turing machine will not work because it will take it a linear amount of time to even find something it's looking for. It has to be random access so that search goes quickly. The uptree is that tree that takes what the broadcasters have to say. It's a competition. The down tree, so the competition takes time. Every match takes a tick. So 1, 2, 3, with 10 to the 7, it turns out that it needs about H for height, 23 ticks for a chunk to get up to the stage. The down tree is bam. It takes 1 tick and is sent to all of the processors. Let me just mention that, as I did mention, and I'll say again, the CTM is not a model of the brain. It's not, but we do make use of what we know of the brain to try to set these numbers right. So 10 to the 7 comes because we have 10 million cortical columns in our brain. And it helps us, choosing the numbers right helps us to make sure we're somewhat on the right track. There are links. These are links between processors. When the CTM is born, there are no links at all. None. 0. Links come in only when a processor maybe asks a question, another one answers it, and the first one says, yeah, that's what I was looking for. And then a two-way link is formed. Okay, so links will get formed in time. Again, this has to do, we've been asked, well, why not just link up everything at the very start? But you can't really. There are 10 to the 7 processors. There are that 10 to the 7 squared, 10 to the 14 possible pairs of nodes, 10 to the 14. But there are only 10 billion neurons. There are only 10 billion axons. The number, or maybe 11 billion, there are only, it's one at most, in the end, at most 1 out of every 1,000 pairs can be linked. So we decided on that account to bring in links only as needed. The inputs you see are real numbers that go to the long-term memory processors, and the outputs come from the long-term memory processors. Well, that's the formal definition. There are two things that we really like. One is conscious attention. What is conscious attention? So we formally define conscious attention to be the reception of the broadcast. When whatever is broadcast is received by all processors see it at the same time, and that which they receive is what they are consciously attending to. And we're pretty happy with that as a definition of conscious attention. We also have this definition of a chunk. So I mentioned that, the input processors take input from the world and turn it into chunks. The chunks are well defined. When George Miller described the chunk, the magical number 7 plus or minus 2, he said, well, what's a chunk? Well, a chunk could be a digit, could be a word, could be even a phrase. And he gave lots of examples, but no formal definition of a chunk. Not till this day do I know of any formal definition of a chunk. Here, we're going to define it formally. A chunk is a tuple, a 6-tuple. It consists of, first of all, the address of the processor that generated the chunk, the time at which it generated that chunk, just this short amount of information that processor wants to get up to the stage. It has to be short. It has to be short to be able to be communicated. You see in front of you what looks to be a nice, complex world, but what is you are actually attending to, what is in the chunk, is something very simple. In my case, I'm seeing an auditorium with people in it, and Lenore is there, and Vanya is over here. So I have a processor. It's very short. It has to be at most 60 characters long. And these characters are actually what we call brainish characters. They're a little more complicated than a word, but words are a good idea. It's like having a 60-sentence word is what a 60-character sentence is what a gist is. There's the weight that I've mentioned, which the weight means roughly how important it is. That takes into account also how sure you are that you're correct, how important it is. One item. There's intensity and mood. Intensity is defined to be the sum of the absolute values of the weights. We take that to mean just how important things are, the chunk is, and the mood is the sum of the weights, which can now be positive or negative. Positive meaning things are going well, negative means not so good. Okay, that's it. And this can be defined formally. Brainish is the language that processors use to speak to each other. We think that the grammar of brainish is going to be like a Creole. Kids essentially make up these Creoles. Creole has words and has a very simple grammar. That's brainish grammar. Brainish words and phrases are multimodal. That's one way in which brainish is sort of more powerful than English or German, whatever it is you think in. Think of brainish as English or Creole, except that the phrase, the red rose, is transformed into what we have here, something soft, red, rose, and the odor of that rose. That's how you would represent the red rose. A gist is a brainish word or phrase of at most 60 brainish characters. Everything the CTM consciously attends to, including its self-awareness, is encapsulated as a gist. The frame of a dream, when you have a dream, most people have visual dreams, the frame of a dream is a gist. A dream sequence is a sequence of frames, each one a gist. Hi, Maxine. The agony of pain is a gist. Have you ever dreamt you had pain? Lenore is telling me we should use fear there because almost everyone has dreamt that at some time that fear. But now I'm working on pain. So have you ever dreamt you had a pain? It turns out that 3% of people recall having a pain in the dream. And of those, roughly half of them, that pain continues after they wake up. The other half, it disappears. And I'm very lucky that I had a dream in which I had a terrible cramp in my leg. It was very painful. And I woke up, and the instant I woke up, the pain was gone. No pain. It's amazing. What? No, the muscle was just fine. No pain at all. That pain was completely the creation of my brain. That's the gist. So that's the second of four. This is very important. How do we check that our model is right? I would love to have something better than what I have, but or better than what we have. We're doing it like this. In order to make sure we're right, we require our model to be just as simple as we can get away with. We call it Occam's razor simple model. It has to be very simple. And anytime someone suggested complicating the CTM to make it do what's wanted, we showed that the changes were not needed. So that's part of it, a very simple model, but it has to be able to do something. And we're very lucky that Kevin Mitchell did propose 15 questions, which he said a good theory of consciousness should be able to answer. So we require that also. We tried a great many models. And for example, we really wanted a deterministic model. We can argue that free will would occur even in a completely deterministic world, that you would have the feeling of free will. There's not difficult argument for that. We tried a great many models and we wanted it to be deterministic, and we could not do that. Here is an example of what we had to go through to try to make it deterministic. You know, to make the model deterministic, we had to suppose you have two chunks that need to get up there, and one has a weight of 100 and the other a weight of 95, and they stay there. Well, in the deterministic model, the weight 100 would get up to the stage, and you'd never see the 95. You'd never see that. And, you know, it can't be. So we had to do something to make sure that the weight of 100 comes down a bit so the 95 can go up. And this is an example of the thing continues. Very complicated. And as I mentioned, when it gets complicated, we threw it out. That's the end of 3. 3 out of 4. Okay, so now we come to the hard problems of pain and pleasure. If you have questions, go ahead. Just yes.
Does each of those 10 million processors capable of producing the whole experience that is presented on stage?
Yes.
Okay, so we have like 10 million. Are we capable of experiencing 10 million more of what we are experiencing?
What gets up on the stage, only one of them gets their stuff on the stage. Only one.
Okay, there is no integration happening.
There's no what?
No integration.
The integration is that whatever gets up there is broadcast. So every processor can include what has been broadcast in its own model. But this, so far, we haven't yet gotten to what really makes for pain and pleasure. So let me keep on going with the hard problems of pain and pleasure, which we have not answered. We're not claiming to have solved the hard problem. Let me be very clear on that. We want to solve it, but we're not claiming to have solved it. So what accounts for suffering? Because I'm into pain, what accounts for suffering? We'll give a very short explanation from conscious attention and then a longer one of conscious awareness. So the conscious attention is what we've mentioned. Conscious attention is what all the processors, the CTM is consciously attending to what the processors receive, to the broadcast. That's what it's attending to. That is what we call conscious attention. And we're very happy with that because, if it were just, even if it's some subset of processors that really accounts for that conscious attention, that subset of processors knows what has been broadcast. Formally, only what relieves the pain can, okay, when pain is over, yeah, pain. Pain, what does the pain do? So in the model, pain interferes with thinking. So what generates the suffering of pain? Pain interferes with thinking. Processors cannot go about their usual business when pain is great. When pain is really great, every processor is interrupted, has to put whatever it's doing on a stack and pay attention to what's in the pain. And every processor is built when there's something very negative up there to put all of its attention on that thing. That's a function of the interrupt. This is very strange, you just broke a leg, you tore a limb, whatever it is that's causing the pain. Just when you need the most to be able to think, you can't think. Every processor is forced to stop, try to see what it can do about the pain. Formally, only what relieves the pain can be given a high enough weight to overcome the weight of the pain. This is built into each and every processor. It is a property of the CTM. The model of the world. So now we get to what is really the important part of what's causing the suffering. Assume that a human has a CTM brain. Throughout this talk, we assume the human has a CTM brain. It doesn't matter if it does or not. There's just a mathematical model. We're not going to even go out and see. It's a mathematical model, and the results are all theorems. But I'll talk in terms of this. A normal human that maybe falls and skins its knee, its model of the world will hold a bloody knee labeled self, meaning that knee belongs to me, and pain, meaning it's hurting. Self and pain. In that case, the CTM has knowledge of its pain. The brainish words self and pain dictate what the CTM feels, but this feeling could be mere knowledge without any suffering. When nociceptors fire, the CTM knows that it has pain, but what accounts for the experienced feeling of pain, the suffering? So we will have an axiom that is not very good yet. The whole explanation will go back to some axiom. The world is being held up by a turtle, which is held up by a turtle, which is held up by the turtles all the way down. We will have to go back to an axiom. Right now, the best we can say is that sensation of pain that the infant had, that pain it had, it felt pain. Whether it's true or not doesn't matter. Something like that is our axiom. So I won't go through this. To understand the suffering from conscious awareness, we have to understand the model of the world. So let's start with this, the model of the world. So the model of the world is all that the CTM consciously knows of the world. The CTM does not actually see the real world, but what it knows is just the chunks that appear in the model of the world. Sensory processors turn inputs into chunks. Motor processors turn chunks into actuations. Chunks are all that processors consciously know of the world. The model of the world is not the world, but the model of the world is all that CTM knows of the world. Different elements of the model of the world are labeled in brainish. Think of labels as something like instantly recognizable colors. So pain would be a color, like red, and self would be another color. There's many, many colors. Just think of it in that way. The model of the world colors its sketches with feelings. These feelings are the qualia of those sketches. Vanya, thank you for asking. Vanya asked, well, how do you define qualia in the CTM? These are the labels attached to the elements of the model of the world. So particularly important for understanding the suffering of pain are self, meaning the sketch so labeled represents a part or the whole of CTM as itself, and pain, meaning the sketch so labeled is in pain. This is self. This is not self. Okay. Vanya, as much as I love him, he's not self. So, okay. The model of the world. When a human with CTM brain skins its knee, its model of the world holds a bloody knee labeled self and pain. In that case, the CTM feels the pain. In general, brainish labels dictate what the CTM feels. But what accounts for the experienced feeling of pain? The brainish word for pain is going to be P0. Remember that infant, there was a processor there that needed oxygen. We'll call that P0. It's the first processor that really puts a big, heavy weight. T0, that's the very beginning of time. P0, T0. P0 is the address of the processor that detected the pain. T0 is the time at which the pain was detected. And P0, T0 enables any processor to pull up the full chunk. The chunk was pain, time, the gist, which it needs oxygen, the weight, how important it was, and some auxiliary information. That cannot be the actual first word, though it's too large. You know, a gist has to be able to talk about pain. A gist cannot hold another gist. So the chunk, the full chunk cannot be the word. The word is just enough information to be able to find that chunk in memory. And that's the processor and the time. So the brainish word pain is P naught, T naught refers to the knowledge of pain. It is a pointer to the brainish chunk, which is the full chunk that originally generated the feeling of pain. The chunk will regenerate that feeling of pain when CTM becomes consciously aware of it. And just why that chunk should generate the feeling of pain, that's currently the best we can do for an axiom. It does. So what account, did I already do this? Felt like it. What accounts for the subjective feeling? The pain was coined in the infant at time T naught, the time that the chunk was generated, plus H, the time it takes to get up to the top of the tree, plus 1, the time to broadcast. That at that time, this was received, and the pain was coined as a word, a brainish, because of the huge weight. As a brainish word, okay, so it was coined then. If the pain at its reception was experienced as suffering, then at any future time, T greater than, okay, so this has to do with why that's an axiom. So we repeat, what might make CTM suffer? There's a pleasure pain axiom still to come, asserting that it will suffer. But why? Why does it suffer? So answer, pain, the brainish chunk that is pain pointed to by the actual word, P naught, T naught, is what CTM was consciously aware of at the time T naught when that chunk appeared, when it had that pain, and would be conscious of again. It would be conscious of again if the gist in whatever this current chunk is contained in it the word P naught, T naught, the pain that it originally had. So why P naught, T naught? It can appear in a gist. Yeah. Okay. Well, the full chunk cannot. Oh, see, this is the most important slide in this talk. What the hell did I have here? Pain is this chunk, is a multimodal brainish generator of the feeling of pain. Because that P naught, T naught, just naught, W naught is what CTM was consciously aware of at the time when it experienced that pain. So it would be conscious of again when aware of it. That's as far as we've gone so far into being able to explain pain. Second most important. That doesn't matter. Okay, what does matter is what arguments can we give for the fact for saying that this is correct? Well, it's kind of interesting. You see, we're saying that the CTM will be in pain when it sees in the model of the world that itself is in pain, when it sees the self and the pain attached to this picture of itself in the model of the world. That's what's behind the pain. So let's ask, what happens if you're missing self or missing pain? So if you're missing self, then the CTM, we're saying, will know that about the pain, will know about the suffering, but it won't be its own. And this is a description of it by a pain asymbolic. There's this one, we're so lucky. There's a disorder called pain asymbolic that you need to know about. Pain asymbolic, a child can be born with it. You can get it from a hit in the head. Pain asymbolic, a person who has pain asymbolic knows about his pain, but doesn't suffer from it. This has been described by a pain asymbolic person like this: when a part of my body hurts, I feel so detached from the pain that it feels as if it were somebody else's pain. You might think that, wouldn't it be wonderful to be pain asymbolic? You wouldn't suffer. But, kids that are born with it, they don't live. By the time they're dead by the age of 3. There was a person who wanted their kid to live, and they had to remove her teeth because she was biting her lips. They had to keep on. She was told, this little kid was told, if you ever notice that you're in pain, take it seriously. Stop what you're doing. Take it seriously. But the kid was out playing ball and was enjoying itself, and so knew that it had broken its leg, but it wanted to play. So now when you see the kid has one leg shorter than the other. Why is this? How are we using this to say that we're on the right track? Well, there are two possibilities. If the body part is labeled self, but not pain, then the CTM is aware of the damage, but does not suffer pain from it. Another possibility is it could be aware, have the label pain, but not self. And that's the case where it knows it has pain of the pain, but doesn't attach it to itself. Both possibilities have been described as pain asymbolic. One of these was the first definition of what's going on. The second one came later, and then there's been some argument about which of these actually accounts for pain asymbolic. What the CTM is saying is they are both possible. There are two possible reasons for pain asymbolic, and both would be described the same way. Good. I just need 3 of them. Okay, so another argument for the correctness of this view: in a dream, a bloody knee can be painful, the pain can persist when CTM wakes up, or the pain can instantly disappear. I already told you about that, right? That I had this pain and that was gone the instant I woke up. The pain in my dream was clearly a manufactured gist. And I have since learned that, yes, I'm not the only one who's had that experience. Oh, that's the end.